Welcome back to Element 14 Presents. I'm Clem and my girlfriend has a new smartwatch that she loves, and I didn't wear a watch for the past 20 years. And I'm certainly not going to wear a watch that is smarter than me. So I'm gonna build myself a dumb watch. So my personal dumb watch will do one thing and one thing only. It will tell the time. Nothing more, nothing less. And before you scream in the comments, oh, just buy a cheap watch and that's it, just a digital little one, that's not the point. I'm building it myself and I'm making it unique. So it's not just a digital watch that just shows you numbers. I want it to have like a unique way of telling the time. When you have it on your wrist, it just sleeps and does nothing, and it just looks like a black monolith. There's not even any hint that this is a watch. But once it wakes up and it tells you the time when you need it to, then LEDs will light up through the surface and then you can see the actual time. Unless you want to see the time, it's completely obscure. Nobody could tell what this thing really is. So I think that's kind of a sleek look, and it's certainly different than other watches. Also, the way it displays the time is a bit special. So everybody knows digital watches like you have on your phone. Most older people like me know analog watches, and I'm sure you also do. And there are other types of watches as well, like binary clocks and stuff where you have to do math to figure out the time. I'm not good at math, but what I'm good at is recognizing shapes at a glance. That's why I was pretty comfortable with reading analog watches. So I mostly consider them like shapes that the little hands of the clock form, and not like where the hands are actually pointing. And I want to put this context into LEDs. So the way you tell time with my watch is by just looking at the shape the LEDs make, and the number of LEDs is the hours on the outer ring, and the inner ring will tell you the minutes to the next 5 minutes to save on LEDs. But if you just look at it at a glance, once you get used to it, you just have memorized the shapes, and the shape just tell you, oh, it's 9:15. I'm restricting the number of LEDs just to make this thing possible to put into a form factor in the amount of time I have. And I also think getting the time to the nearest 5 minutes is really enough for your daily life. We're already like so fed up with constant pressure and constant getting everywhere on time and keeping schedule that 5 minutes is something that you should be able to like vary. Don't pressure yourself. It's like slow food. Just slow watching, slow timekeeping. You get the idea. Relax. I set myself some size goals. So I don't want it to be thicker than 10 millimeters, and I also want it to be smaller than 60, maybe 50 millimeters in diameter. Just so it stays within the size of a normal watch, a bigger one, but it's still a watch and not like a big hunk of plastic that you put on your wrist. Instead of going with a huge modern overpowered MCU, I'm using maybe the smallest possible thing, not really the smallest possible, but certainly a very cheap and affordable one, a simple microcontroller, a small one, and also something that has like some restrictions on there, but also has some advantages for such designs. I'm using an ATtiny 412. I'll explain why. The ATtiny 412 is a new ATtiny processor that uses UPDI for programming. We've made a UPDI programmer in a previous episode. That's basically what we're using to program it. But because those programmers are so simple, we could also have the chance to integrate that into the device. So you plug it in, can charge it, and also reprogram it if you want. Or set the time, maybe. The ATtiny 412 only has 8 pins, so it's really compact, it's easy to solder, and these restrictions also let the creativity flow, because we have to basically interface 24 LEDs to maybe like 3 pins. So we have to get creative on that one. Also I need charging on board, regulation and stuff, and of course a real-time clock. I could just like clock pulses on the microcontroller, but in reality you will want to have a real-time clock. And this device should also not run all the time, but the clock module basically gets a battery backup, and whenever the microcontroller boots, it gets the current time from the clock module and displays it. And if I turn the watch off, the clock still keeps the time, even though The rest of the system is off. When you look at the schematic, you will see the obvious culprits. You see the microcontroller that we use. We also have a real-time clock chip on there with its own crystal. So that crystal is basically keeping the time while it's running. The real-time clock has its own connection to the battery, which is a lithium-ion button cell, an LIR2450. And this cell is charged with its own dedicated charging controller. It has a protection circuit on there, so we can't overcharge or over discharge it. And it's directly connected to the RTC. And with a switch, it's then connected to the MCU. There is no voltage regulator inside. This means we don't have any conversion losses, which makes the whole thing a bit more efficient, but it also means that our voltage levels that we have in there, or our reference levels, will change depending on the depletion of the battery. So there will be a point where the RTC still can keep the time, but the MCU is no longer able to boot or to display the LEDs because the battery is already so drained. This is something that we can actually use to our advantage, not disadvantage. To display the time, we have to interface 24 LEDs with our MCU. We only have 3 I/O pins. So what are we doing? Multiplexing, charlieplexing? We could do that if we had a bit more I/O. But what I want to use this time is shift registers. I have 74HC595 registers, 3 of them. 3 exact because 3 of them give us exactly 24 outputs. And those 24 outputs, 24 hours, or as well 24 LEDs, 12 for the hours, 12 for the minutes. The 60 minutes divided by 12 gives us 5, and that means the clock is accurate to 5 minutes, which is also the division that you usually see on an analog clock. So that kind of makes sense. The code for this project was quite tricky. We have to interface the RTC clock with the MCU over I2C, and we only have an ATtiny. The wire library on Arduino does not work for that because it's just too big. We don't have any space left if we use that. So I had to resort to 2 things. I can't use the dedicated library for my real-time clock chip, and I can't use the wire library that you usually would use together because there's no space for that. What I can use is, there's a tutorial I found by Reingold Heavy that explains how you can interface with that chip by directly calling the registers. So I don't have to use the library anymore. Now I have a different problem. I need to then use a different library for I2C. There's a special ATtiny I2C implementation. So I get that in, and now I have to rewrite all these commands that I saw in the tutorial for that library. That was quite tricky. Also, there are some registers that you have to set in weird ways, and you have to, it was a bit of a nightmare thinking around all this stuff. It is way too long for just this video. If you want a video on how you make these I2C devices work and stuff with directly calling the registers, please let me know in the comments and we'll do that video. It's just too big for now. Okay, once we have our current time, we have to split that into hours and minutes. Forget about the seconds, we don't need those. And then we have to clock them into the shift registers. What does clocking in mean? What does that even mean? Well, you have a clock pin and you have a data pin. Whatever is on the data pin, when you pulse the clock, that value gets fed into the shift register. So if there's a 0, pulse 0. There's a 1, pulse 1. Now there's 1 0 in the register. The rest of it is just random data from before. So if you want to have a clean start, pump it full with zeros. We have 24 places in our 3 74HC595 registers that are ganged up in serial. So the output pin of the last one is the input pin of the next one. And if we just pump them full with zeros, like 24, or just do 25 so you can be sure they are completely full with zeros, then the clock is basically cleared. And then we clock in our minutes first. This is because I hooked it up in a way that the minutes will have to be displayed first and then the hours. So I'll take the number of LEDs that I have to show. So if I know my minutes, let's say it's 30 minutes, 30 divided by 5, is that 6? I think it's 6. And then we have to pulse the clock pin 6 times while keeping it high. So 1, 2, 3, 4, 5, 6. Now 6 beats are LEDs that are light up. And then we have to set the data pin low and clock it for the remaining bits of the minute. So 6 more. So we clock in 6 more, and now we have 6 set bits, 6 empty bits, and now we're setting the hours in the exact same way. That is basically the same data, just serialized and put into that with the minutes first and the hours second. And nothing is showing because we also have to enable the latch pin, like the output enable is hardwired to be enabled, but there's also a latch clock. If you pulse that, then all the bits that are currently clocked in gets put on display and the clock will show up. And this means that you won't see the bits shifting when we clock them in. You will only see the outcome when we finally enable the display. Now that I think of it, seeing how the bits clock in and stuff, that could make for pretty cool animations and stuff. And maybe we could build like a really weird display with that. Let me know in the comments if that's a project that would interest you. That might be pretty cool and weird. So with the assembled PCB, I now have to program it, of course. I tried to integrate the UPDI programmer by just using a serial to USB bridge inside. And with a little switch, I can connect the RX and TX pins together over a series of resistors and diodes and put that to the UPDI pin. And it doesn't work.
Hello, I'm James from Workbench Wednesdays, a show about the stuff found on your electronics workbench. Look for new episodes on, well, Wednesdays. You can connect with me over on the Element 14 community. I look forward to seeing you. For now, it is time to get back to watching this week's project video.
Okay, so it seems like I didn't build the UPDI programmer correctly in there. So now I'm using an external UPDI programmer. I use one that Arduino makes, and I also put that on my store so you can have it because it's pretty good. It also works on ESP and stuff. I tried it with that one, and that did directly work. So I asked him for the schematics and stuff, and he basically uses a 5.1K resistor to connect those, and I used the diode variant and whatever. Maybe I don't have the right diode for that one. But I also tried replacing my setup just with a resistor, also 5.1K, and it didn't work. And then I found out that, yeah, sometimes you have to tweak that value. Usually the tutorials tell you to use a 4.7K ohm resistor. I don't have one of those in stock, curiously. Yeah, but usually that value is also dependent on like the resistance of the contacts and the traces and stuff, so you have to maybe play a bit around with that value. And it seems in my construction that value won't do the trick, so I have to resort to the external programmer. Speaking of having it programmed, we now have another problem, a very weird one. So at the moment it doesn't look like I can really interface with the real-time clock. Yeah, that's pretty bad. It shows up when I use an accuracy scanner script, and it just tells me its address, which is correct. Everything is there where it should be. I can set it, so it perfectly fine reacts to all the settings and stuff, but it doesn't seem to run. It never changes. I left this for hours and it does not change. So my suspicion is that the clock is actually not running, or the oscillator on there is not running. Maybe I've messed up the loading crystals or something else. So I googled around, what could it be? It seems that a lot of people have trouble with this particular chip. In the tutorial that I followed for interfacing it directly with calling the registers, it tells me that you have to set a specific bit to engage it. And I think I'm setting that bit correctly. So my next guess is I've done something that you shouldn't do with these crystals. I've cleaned the PCB in an ultrasonic cleaner like I always do. yeah, if you're using a crystal on there, don't put it in the ultrasonic cleaner, it can damage it. And I think that is what happened. So I'm gonna replace the crystal, see if that changes anything. If that doesn't, I'm also gonna change the RTC clock IC and see maybe that was damaged. So we'll start from there then. You know what really sucks? When you think you have found the culprit and it didn't change anything. It's still exactly the same. So I've gone through the tutorials more and more, and it just told me, yeah, tell bit 7 to be 1, and then it just occurred to me, yeah, I do that on setup. All these setup registers are intertwined with the register that set the hours and minutes. And when I set the minutes, I basically override that. So that bit is set, and then it's unset again once I set the minutes. And if I then set it again, then just on its own, then of course all the other data is gone, because I can only like write a full byte. I cannot like just write one bit of that byte. I always have to write a full byte. So I had to get in my head that I need to do math, and I hate math. So you have to binary add the values that you need and then write that bit. This took me forever to figure out, but also you don't just add by doing the plus, you add binaries by doing a logic OR. And that is basically what I did wrong. And turns out, once you did the right calculations and you wrote that byte, now the thing runs. So maybe the crystal wasn't even broken after all. I don't know. I've exchanged it, it's now running. I'm just happy that this thing works at all. So while I left the clock running to check if it actually displays time passing, so I could only see changes every 5 minutes. And of course, if I just let it run, then the battery might drain too fast. So I just check it every few minutes or so. And also I can't just leave it charged, because the way I designed it makes it like the actual level references change depending on the charge state of the battery and how it's charged at the moment. So when you plug in the USB cable for charging it, then basically the LEDs just go in wonky patterns and stuff. So you won't really see the time passing on there. Well, that's a design flaw. But it actually does pass the time. And while I'm doing these tests, I'm designing a case for it. I actually did the case design process a few times until it fit. I had to do a lot of iterations. Originally, I wanted to use these wristbands. These are made from silicon. I got them pretty cheap, and I have a lot of those, so I thought, hey, if that clock is really popular, maybe I can make a kit out of it. But turns out, if I put that in, it's just gonna be too big. So for now, at least for this iteration, I'm resorting to some straps, like Velcro. And I can just easily put that on my wrist. And you see that sleek looking case? It's just a black circle. That is resin print. It's printed with my MX engineering resin. The back is translucent, so you can see what's going on. And you can just lift this off, and then you can see the bare PCB. And when it's on, it shines through the case. Isn't that nice? It took me a while to get there. So I had to do a lot of revisions and tested how to spray paint these and how to finish them with sandpaper and stuff, so to make them like really shiny and smooth. And it turns out that's great. It's all printed in my MX engineering resin, so these are sturdy as you can ever get a resin print. And yeah, it's basically like injection molded. So that's a pretty good prototyping material, especially if you make weird stuff like this. So my watch is finished. It's just a sleek, flat circle. There's no way you could tell this is a watch, but just looking at it, it could also be like an emergency button or like some access control thing like NFC stuff. You couldn't tell. But if you turn it on, then you can see the LEDs shining through the case. So you can tell I took the footage in various times in the day, and currently this displays the time as it's 5 minutes past midnight. So it's 5 minutes AM. it took a while to get it going. But you can see the outer ring, and you can see the LED in the middle. This seems a lot more comfortable than I expected. So the wrist strap, the Velcro, is like any other watch band. I pretty don't mind it. And yeah, it's a big thing. Like, I would wish this was a little bit smaller, but it's already a 4-layer board and I really couldn't fit it into any smaller form factor, at least on this iteration. Maybe I make another one and then I could be smaller. Also, if you want to make your own version, you could make it smaller. All the files are on the Element 14 community and they're free. So knock yourselves out and make dumb watches. I didn't want a smartwatch, so I built a dumb watch. It just tells the time and it's, oh wow, it's really late. So head on over to the Element 14 community, let me know your ideas to make this better or other projects that we could tackle. You can also go there to interact with me and the other hosts on there and download all the files for free as always and find all the parts that you need to build such a thing. I gotta go. There's another project waiting for me. Also, it's very late and I need some sleep.